Alright folks, today we're going to be working a little bit with free body diagrams. What free body diagrams are ways to draw all the forces acting on an object so that you can use these forces to determine what's going to happen to the motion of the object. For example, if all the forces cancel each other out, so the total net force is zero, well, with no net force, the object will not accelerate. It'll stay at whatever constant speed it was moving at, even if that is a speed of zero. If the free body diagram shows that it's being pushed harder in one direction than another, then the net force is in the direction of the larger force and the object will accelerate in that direction. So we've got a few different examples here for you, just talking about some different common situations that you might encounter. So the first one, we'll start out with the most basic. We're talking about a falling object. So in this case, we're saying there's no air resistance, so there's no air pushing on it as it falls. Now when that happens, there's only one force pushing on it, that's the force of gravity, and so that would cause the object to have a force pulling it downward. You can call it the force of gravity. In another video we watched, we called that the force of your weight. So in this case, the free body diagram is very simple. It's simply the force of your weight pulling you down. We do want to remind you of an equation that you had learned earlier in one of the other videos from when we were still in school but I was absent, and that was, you do know how to calculate the weight. We're just going to give you a quick reminder here that the force of your weight is equal to the mass of the object times the acceleration of gravity. And if you forget that, just a quick reminder, that would be mass times the acceleration of gravity is negative 9.8 meters per second faster every second it falls. So the mass could be measured in kilograms. So if this is a 20 kilogram object, multiplied by the acceleration of gravity, and that would give you how many newtons of force are pulling it down due to the weight of the object. Now the net force vector, if we say all the forces acting on it, what do they add up to be? Since there's only one force, this is really basic, then the net force is down. In this case, the net force equals the force of your weight. Second situation right here, you've got an object that's falling. Oh, actually we forgot, what's the resulting motion? The resulting motion is that the object accelerates down at 9.8 meters per second faster every second, which we can abbreviate the acceleration of gravity as g. In the next example, you have an object falling, but there is air resistance, which means, yes, you've got the force of the object's weight, the force of gravity, pulling it down. However, as it falls faster, you feel a force of the air pushing you up, much like when you put your hand outside of a window as you're driving. And so you do have the force of air resistance pushing up. Now I'm going to make that a smaller arrow. In other words, we're saying the weight pulling you down is bigger than the air resistance pushing you up. And how am I going to abbreviate air resistance? I'm just going to put a little AR for air resistance. So in this situation, the downward force of your weight's bigger than the force of air resistance. So therefore, the net force for the would be down, but it's not as big as it was before. Before you had a larger, because it was your entire weight. Now part of your weight is canceled out by the air resistance. So here's your net force. You're still going to accelerate down, but not as quickly as you would if there had been no air resistance. And that's what we have written down right here. The object accelerates downward, but less than 9.8 meters per second per second. In other words, the acceleration of the object is going to be less than the acceleration of gravity when there is air resistance to affect it. Now the third situation we have here, let's move this up a little bit. This situation talks about an object falling at a terminal velocity. Now just to make sure that you understand what we mean by terminal velocity, it's the maximum speed the object's going to reach when it falls. And basically this happens when the force of the air resistance that pushes up, so in this case you do still have the force of the weight pushing down, but now it's falling so fast. As it fell faster, the air resistance got bigger and bigger and bigger. Well, there comes a point where if you fall for long enough when there is air resistance, that the air is pushing you up, force of your air resistance is pushing you up with just as much force as your weight is pulling you down. Now when that happens, what's the net force? In that case, the net force is going to be zero. In other words, the forces are equal opposite, they cancel out. And what happens when the forces cancel out, that doesn't mean you stop. It means that the acceleration is going to be zero. And when the acceleration is zero, that means you stay at whatever speed you're going. And that's why they call this terminal velocity, is because that's the highest speed you're going to reach. Once the air resistance pushing you up equals your weight pushing you down, then you stop accelerating and you stay falling at that constant speed. And so the resulting motion, we can read that as an object falls at a fast but constant speed. There is no acceleration. Now, that brings to mind this situation, number 4. The object's falling with a parachute. Now, that would also be terminal velocity, but you may have wondered, like, what's different about it with a parachute? What a parachute does is it increases the force of the air resistance when you're moving at any speed. So basically, we have the same situation as before. You have the force of the object's weight pulling you down, but when this force of air resistance is equal and opposite, that's going to happen when you have a parachute at a slower speed. The air resistance is greater at slower speeds when you've got a parachute. It simply catches more air to push you up. So the net force and the acceleration are the same as before because you're at terminal velocity. Your speed is no longer increasing. You're falling at a constant speed. The only difference is when in this situation without a parachute, you had a large velocity. You had to fall very fast before the air resistance equals the weight pulling you down. When you have a parachute, this happens at a slower velocity. So why do you want a parachute? Turns out you'll reach terminal velocity if you jump out of an airplane that's flying high enough. You'll reach terminal velocity either way, but would you rather hit the ground going at a very, very fast speed, or would you rather have your top speed be slow by deploying the parachute? Either way, we say your terminal velocity. It's just the parachute makes it a slower velocity. That's the maximum speed that you reach. And that's what we have written down here. The object falls at a slow but constant speed. Here it was a fast constant speed. Here it's a slow constant speed. But in both cases, once you hit terminal velocity, there's no more acceleration. You keep going at the same speed. Moving back up to situation number 5. An object sitting on a table. Well, that's a really simple situation. Now, some people might think, well, then the only thing that's pushing on you is your weight, the force of gravity. But that's not exactly true. If this is the only thing pushing down on you, well, then you'd have the same situation as you had up here, where the only force is pushing you down, so you'd accelerate down, and you'd be falling. So when you're sitting on a table, you're not falling. What else is pushing on you? Well, the object's weight makes it push against the table, and when it pushes against the table, then the table pushes back. That's Newton's third law. When you push on something, it pushes back with an equal amount of force. So there's an equal amount of force here. So gravity's pushing it down, the table's pushing it up. If we draw these at the same length, now what do we call this? You could say it's the reaction force from Newton's third law. For every action force, there's an equal opposite reaction force. However, they give this a name. They call this the normal force. In math class, normal means perpendicular, and this force is usually 90 degrees to the surface of the table. But in any case, those two forces are the same, and so when you add them up in opposite directions, you got a positive force up here, a negative force down here, you end up with a total net force of 0, and whenever the net force is 0, then your acceleration is 0 as well. So in this case, the object stays at a constant speed. It just happens to be that here the constant speed is 0. In these other situations where it was heading at force of 0 and acceleration, it was moving when that happened. Here it wasn't moving, and with no acceleration the speed won't change, it stays stopped. And again, Fn right here, if we go ahead and just write that out, Fn is called the normal force. And again, just a reminder, when you push on something, it pushes back. So when the object pushes down on the table pushes back up with an equal amount of force. Those two forces cancel out to stop the object from accelerating. Now, in situation number 6, the object is being pushed forward and it's speeding up. So what forces are acting on it? Now we're talking about, we're going to have a forward force, that's right. But don't forget, we're still on Earth, we still have gravity. So you still have the force of the object's weight in any situation, unless we say, oh, you're out in space and there's no gravity acting on you, you're far away from any planets. There's always going to be the force of gravity, your weight pulling you down. But since it's on the table is going to push back to support the weight to stop it from falling. So you still have that normal force pushing back. So those two cancel out. There's no upward or downward acceleration. But in this case, it says you're being pushed forward and it speeds you up. So there is a force, and I can write P for push. Right now, I'll just go ahead and write out the whole word. You've got the force of the push pushing back. Now, when something slides across the table, when this slides across the table, you hear that noise. That noise is the friction, and friction always pushes you in the opposite direction you're moving. So there would be a force of friction pushing backwards on this. And we're just going to abbreviate the force of friction as F with a little subscript, lowercase f. Now you notice I made the forward push larger than the backward force of friction because we said it's going to be speeding up. So if you want to speed up, you're accelerating, so you need the force in the direction you're accelerating to be larger. So in this case, those two forces canceled out. If you add these two up just by looking at the sizes, this one's bigger. So there is a net force pushing you in the direction of the larger force. And that means you always accelerate in the direction of the net force. So we can go ahead and read the object accelerates to the right and it's speeding up, it's accelerating. Looking at number 7, the object is sliding to a stop. So again, we're on a table. So as usual, we have your weight pulling you down, the table supporting you. So you have an equal normal force pushing you back up, Fn. But it says you're moving and you slide to a stop, so we're no longer pushing forward. It's sliding to a stop. Why is it slowing down? What force is making it accelerate? Well, we got rid of the push, but we haven't gotten rid of the friction from above. Before we were pushing it forward, friction was pushing it backwards, and those two forces are kind of fighting against each other. But now, if we don't push forward, the only force that's still pushing it sideways, we still have that same force of friction pushing backwards. So those two cancel out. You got a force pushing backwards. That means that the net force is going to be pushing backwards. And when the net force pushes backwards, you always accelerate in that same direction. So we can say for its motion that the object is going to accelerate to the left, but this time the acceleration is going to be negative. The object, instead of speeding up, it's going to slow down. And then finally here in number 8, the object's being pushed forward at a constant speed. So in this case, we have our weight pushing down, the normal force from the table pushing up, and we're pushing it forward, but it's moving at a constant speed. And what would that mean? That means if we have the force of our pushing forward, if it's not accelerating, all the forces must have canceled out, so there must be an equal amount of force pushing back. So we got our force of friction pushing back, our the force of our push pushing forward, they're the same. Therefore, the net force would be 0, and then the acceleration would be 0. That satisfies the situation. We said it's going at a constant speed. So it does have a velocity this way, but because the forces cancel out, it's not going to be accelerated forward, it's not going to be accelerated backwards, it's going to stay at that constant speed. And we can say that the object moves forward at a constant speed, there is no acceleration. Now we just have a few more on the back side of the paper, so let's go ahead and show you those. So what we have here is an object that's hanging from 2 ropes. So you've got the force of gravity, the object's weight, force of your weight pulling you down. Now it's hanging from 2 ropes. I just wanted to show you this situation. You could draw one force pushing up that's equal, holding it up, holding it steady. But if it's 2 ropes, you could draw it this way where you've got a small force of, let's say, rope 1, and you have another small force of rope 2, and those two add up to be an upward force that's equal to the weight down. So then what happens? Well, if an object's hanging, you understand it's not accelerating, it's just sitting there, it's got a constant speed. The net force must be 0 because there's 0 acceleration when it hangs. So again, these two forces are going to add up to be equal to the weight. It's just, since there's two ropes, well, you can divide it up into half the weight here and half the weight there, pulling up to cancel out the weight pulling down. Same thing could be said if you're on a swing. Each rope on the swing holds half of your weight. If you're doing the monkey bars on the playground in elementary school, then you're supporting yourself by 2 arms, and each arm holds half your weight. You realize that because if you take one of your arms and let go, you would be supporting yourself with 1 arm, and then that would have to support the whole weight. That's much harder. By using 2 hands, you divide the weight in half for each hand. It's easier to hold your body weight up that way. So we say the object stays at a constant speed of 0. There's no acceleration because the force is canceled out. It wasn't moving before. It's going to stay not moving because there's no acceleration. So the speed equals 0 and it stays constant. Second to last situation here, an object is being lifted upward and it's speeding up. So as an example, if I hold my pencil, right now it's sitting still. When I push up, well, I have to make it accelerate upwards to give it some speed. So you've got the weight of the object, the force of its weight, but to make it accelerate upwards, you have to push harder up than it's being pushed down. So we would draw a larger force. And again, if I push on the pencil, it pushes back down. So I'm pushing on it with a lot of force, and so its weight doesn't change, but I pushed upward with a large force. So this force is bigger than that. So the net force is going to be in the upward direction, and whichever way the net force is going to be the direction of the acceleration. And that's why when you first lift an object up, it speeds up. You have to push with more than it weighs. And here we can see the object accelerates upward as it speeds up. Now, let's imagine that once you get it going, you just lift it at a constant speed. Well, if you lift it at a constant speed after you've already got it moving, then it's not accelerating. And remember, the only way to have no acceleration is for the forces, any forces on it, to be equal and cancel out. So when it's moving at a constant speed, you've got the force of your weight pulling down, you've got that normal force pushing up. Those are equal and opposite. So the net force is 0, but that doesn't mean it stopped. It just means that the acceleration is 0. The speed isn't changing. So once I get it moving, I don't have to push quite as hard. I just have to push equal to its weight up. And that means it won't change speeds. The object is going to move upward at a constant speed. There's no acceleration. This also happens if you think about an elevator. If you've ever ridden an elevator, which, let's face it, all of you have, when the elevator first starts out, you were stopped, you accelerate upwards, and you feel, just for a moment, you feel heavier because you're being pushed harder than your weight up. Instead of being supported by equal to your weight, you're being pushed upward harder than you weigh, and it makes you feel a little bit heavier. But once you're up to speed, you don't feel as heavy the entire elevator ride, because once you get up to speed, the normal force pushing you up is equal to your weight, and it just keeps you going at that speed. Now, I didn't draw it, but think about what happens at the end of an elevator ride. At the end of an elevator ride, for a moment, when you come to a stop, you feel lighter. What's the reason for that? Well, to slow you down, if you're going up, to slow you down, you have to have a net force pushing you downward to accelerate you in the negative direction. So what happens when you come to a stop in an elevator is the normal force actually becomes less. It stops pushing you up as hard, so that acceleration downward stops you, slows you to a stop, and at that point you weigh the same again. And that is your lesson over drawing force diagrams.